Uh, hey gang, Math 5500, intro to multiple regression. The great thing about multiple regression, aside from a couple of caveats, is if you've understood fairly well, especially matrix operations for simple linear regression, then the transition into multiple regression, again, aside from a couple of things, let me get rid of my board meeting reminder. So, let me get this. This is kind of off a little. That bugs me. Okay, so anyway, moving into multiple regression, the expected value for our y sub i's is just going to be beta 0 plus beta 1 x1 plus beta 2 x2 plus beta sub p minus 1 x sub p minus 1. Sorry, I can't see when I get way over there because my document camera is way over to my right. So anyway, so if we have p equal, whatever, 3 predictors, then the expected value for y sub I would be beta 0 plus beta 1 x1 plus beta 2 x2 according to this. Now, well, no, let me go ahead. So what we have here is we have, 3 parameters, beta 0, uh, beta 1, and beta 2, of course, predicted by, or I should say estimated by, beta 0 hat, or B0, beta 1 hat, or B1, and beta 2 hat, or B2. So our model, therefore, if we look at it in terms of just y sub I, this is beta 0 plus beta 1 x sub I1 plus beta 2 x sub I2 plus beta sub p minus 1 x sub I p minus 1, of course, plus the error term. So, ladies and gentlemen, this is flashing neon lights around that part. That is our model. Now, a few differences. First of all, unlike simple linear regression, where our lone sole predictor had to be quantitative, when we move into multiple regression, this is one of the caveats of transitioning from simple linear regression to multiple regression, is that our predictors can be categorical. So it again adds adds flexibility, adds power to the technique, but it also adds a couple of caveats. Now, I will say I think that this whole p minus 1 predictors is clumsy, and you see most textbooks in advanced regression use this language. And again, I think it's slightly clumsy. If we, for example, are going to, and let me explain this. If we're going to predict, for example, first-year college GPA from maybe high school GPA plus, an ACT plus maybe first generation status. Well, no matter how you twist this or adapt the narrative, I think we have 3 predictors, right? So with our 3 predictors, we're going to have 4 estimates. We're going to estimate beta 0. We're going to estimate the coefficient for the high school GPA, the coefficient for ACT, and the coefficient for first gen status. Now, tattoo that one to the brain temporarily, because as we move into bigger stuff, we're going to find out that we're going to have categorical variables with more than 2 levels. We have to create k minus 1 dummy variables. So anyway, that's going to take a different form once we get there. But for now, okay, for now, if we have 3 predictors, we're going to have 4 estimates. Now, the beauty of all this is, in terms of matrix operations, very little changes. For example, what does my response vector look like? Well, it looks like my response vector from simple linear regression. What does my design matrix look like? Well, it's still, just like simple linear regression, starts out with a column of 1s. And the next thing we will have is we'll have our x11, x21, down to xn1. We'll have our column of our x's for the first predictor. And then we'll just keep doing this until we get to our... So this would be for the p minus 1. Again, it's hard to see way over there. So we'll have that final column for the last predictor. Turns out that, if we, like in the previous example I gave over here where we had 3 predictors, then we're going to have 4 columns. So specific to the previous example, my design matrix would look like 1s, x11, x21, xn1, x12, x22, xn2, and x13, x23, xn3. So my column of 1s, my next column is the x's that would be for the high school GPA. This would be my ACTs, and this would be the first gen status, classified in terms of 0s and 1s. Can't put yeses and nos in a matrix for obvious reasons. What does beta look like? Well, beta is going to be calculated just as before, but your beta matrix is going to be your beta 0, your beta 1, and your beta p minus 1. What are your errors going to look like? Well, just like before. You're going to have an error term for each observation, each sub I. And these errors are still going to be independent, and they're still going to follow a normal distribution, mean 0, variance sigma squared. What's the hat matrix going to look like? Same thing as before. And what's the hat matrix going to do? Well, it's still going to project our predicted values. It's going to project our observed y's onto our predicted, and it's still going to serve as a diagnostic measure. Easy for you to say. So again, the great part of all this is much of what we learned, we really don't modify much. Really the only modifications will be the design matrix is going to have more columns, and our beta vector will have more entries because we have additional coefficients that we're estimating. Now I want to get out of here and just get the ball rolling a little bit. look at an example and give you some just some very basic stuff information.